Hey there, science fans! Have you ever thought about the invisible forces that shape our world? Force is what makes things move, stop, or change direction. It's what holds structures together and allows us to interact with our surroundings. We experience force every day, from the simple act of picking up a book to the powerful thrust of a rocket launching into space. Understanding and measuring force is crucial in countless fields. Engineers rely on force measurements to design safe and durable buildings, bridges, and vehicles. Doctors use force sensors to monitor muscle strength and diagnose medical conditions. Even athletes benefit from force plates that analyze their jumps and strides. So buckle up as we embark on a journey into the fascinating world of force measurement. Measuring force is like solving a puzzle. We need the right tools for the job. Over the centuries, scientists and inventors have developed ingenious instruments to quantify this invisible force. One of the simplest and most recognizable force measuring devices is the spring scale. Remember those hanging scales at the grocery store? They use a spring that stretches or compresses in proportion to the weight of the produce. For more precise measurements, we turn to sophisticated devices like load cells. These marvels of engineering use electrical resistance, strain gauges to detect tiny deformations caused by force. They're like super-sensitive electronic springs. Strain gauges are thin, flexible circuits bonded to the surface of a material. When force is applied, the material and the strain gauge deform slightly. This deformation alters the electrical resistance of the gauge, which a clever circuit measures and converts into a force reading. To truly understand force measurement, we need to delve into the fundamental laws of physics that govern it. These laws form the backbone of how we quantify and interpret forces in various contexts, from everyday activities to complex scientific experiments. Sir Isaac Newton, the OG of motion, gave us his famous second law: force equals mass times acceleration, F equals sine ma. This groundbreaking equation revolutionized our understanding of how objects move and interact. This equation tells us that the force applied to an object is directly proportional to its mass and the acceleration it experiences. In other words, the heavier the object or the faster you want it to move, the more force you need to apply. So pushing a heavier object or making it accelerate faster requires more force. This principle is fundamental in fields ranging from engineering to sports science, where understanding force and motion is crucial. But what about those spring scales and load cells? These tools are essential for measuring force in a precise and reliable manner. That's where Robert Hooke's law comes in. Hooke's contributions to the field of mechanics are invaluable, particularly his work on elasticity. Hooke's law states that the force needed to extend or compress a spring is proportional to the distance it is stretched or compressed. This principle is crucial for understanding how materials deform under various forces. This relationship is often expressed as F equals sine kx, where F is the force, x is the displacement, and k is the spring constant. The negative sign indicates that the force exerted by the spring is in the opposite direction of the displacement. Load cells take advantage of this principle by measuring the tiny deformations caused by force, which are directly proportional to the applied force. These measurements are critical in various applications, from industrial machinery to scientific research, ensuring accuracy and reliability in force measurement. Ready to see a load cell in action? Let's set up a simple experiment to measure the force exerted by a weight. Materials: a load cell with a digital display, a stable platform or fixture, a known weight, for example a calibrated mass, and connecting cables. Procedure 1. Mount the load cell securely to the platform, ensuring it is properly aligned. 2. Connect the load cell to the digital display using the provided cables. 3. Turn on the display and allow the load cell to stabilize. Note the zero reading. 4. Carefully place the known weight onto the load cell's sensing platform. 5. Observe the digital display and record the force reading. 6. Repeat steps 4 and 5 several times, carefully lifting and replacing the weight each time. By averaging the force readings, we can minimize random errors and obtain a more accurate measurement. Section 5. Crunching the numbers, making sense of force data. In this section, we will delve into the process of interpreting the raw data collected from our experiments and transforming it into meaningful insights. Raw data from our load cell experiment is just the beginning. This data, while valuable, is essentially a collection of numbers that need to be carefully analyzed. To extract meaningful insights, we need to analyze and interpret the numbers. This involves using various data analysis tools and techniques to understand the underlying patterns and trends. Let's say we placed a 10-kilogram weight on the load cell, and the average force reading was 98 newtons. This is a crucial step in our analysis, as it provides a concrete example of how the data is collected. This result aligns with Newton's second law, which tells us that the force exerted by an object due to gravity is its mass multiplied by the acceleration due to gravity, approximately 9.8 meters per second squared. Understanding this law helps us validate our experimental results. We can present our experimental data in a clear and organized manner using a table. This makes it easier to compare and contrast different readings. Trial 1, force reading 97.8 newtons. Each trial provides a slightly different reading, which is expected due to minor variations in the experimental setup. Trial 2, force reading 98.2 newtons. By recording multiple trials, we can ensure the reliability and accuracy of our data. Trial 3, force reading 98 newtons. Consistency across trials is key to drawing valid conclusions from our data. Trial 4, force reading 97.9 newtons. Small variations are normal and can be accounted for in our final analysis. Trial 5, force reading 98.1 newtons. By averaging these readings, we can get a more accurate representation of the force. The average force reading is 98 newtons. This average helps us summarize our findings and provides a reliable measure of the force exerted by the 10-kilogram weight. Section 6, Error Alert, identifying and minimizing measurement mistakes. Even the most sophisticated force measurement systems are susceptible to errors. Understanding the common sources of error is crucial for obtaining accurate and reliable results. One potential culprit is calibration error. Just like a musical instrument needs tuning, force measuring instruments require periodic calibration to ensure they provide accurate readings. Environmental factors can also wreak havoc on force measurements. Temperature fluctuations, vibrations, and even air currents can influence readings. To minimize errors, it's essential to calibrate instruments regularly using known standards. Control environmental conditions as much as possible and use appropriate data filtering techniques to reduce noise. By being mindful of these factors, we can improve the accuracy and reliability of our force measurements. Section 7, Force Measurement in Action, from Bridges to Biomechanics. Force measurement plays a vital role in countless real-world applications. It is the backbone of many engineering and scientific endeavors, providing critical data that informs decisions and ensures safety. Let's explore a few fascinating examples that demonstrate the breadth and depth of force measurement technology. In civil engineering, engineers rely on force sensors to monitor the structural integrity of bridges, tunnels, and buildings. These sensors help detect stress and strain, providing early warnings of potential failures. By measuring the forces acting on these structures, engineers can detect potential weaknesses and ensure public safety. This proactive approach helps prevent catastrophic failures and extends the lifespan of infrastructure. In manufacturing, force measurement is indispensable. It ensures the proper clamping force in assembly lines, controls the tension in materials like fabrics and plastics, and maintains quality control throughout the production process. In the field of robotics, force sensors provide robots with a sense of touch. This capability allows them to interact with delicate objects and perform tasks that require precise force control, enhancing their functionality and versatility. In biomechanics, force plates embedded in floors or treadmills allow researchers and clinicians to analyze human movement patterns. This technology is crucial for assessing athletic performance, diagnosing gait abnormalities, and developing rehabilitation protocols. These examples highlight the diverse and essential role force measurement plays in our technological world. From ensuring the safety of our infrastructure to advancing medical research, force measurement is a cornerstone of modern science and engineering. Section 8, Precision Matters, ensuring accurate force readings. The accuracy of force measurement systems is paramount in many applications. Inaccurate readings can lead to design flaws, product failures, and even safety hazards. To ensure precision, Manufacturers of force-measuring instruments invest significant effort in using high-quality materials and manufacturing processes, implementing rigorous testing and calibration procedures, and providing detailed specifications and traceability documentation. By adhering to strict quality standards, manufacturers ensure that their instruments meet the demanding requirements of various industries. Section 9. The future of force innovation and beyond. The field of force measurement is constantly evolving, driven by advancements in sensor technology, materials science, and data analysis. Researchers are exploring new types of force sensors, such as flexible and wearable sensors that can be integrated into clothing or medical devices. These innovations promise to revolutionize fields like healthcare, sports science, and human-machine interaction. As technology continues to advance, we can anticipate even more sophisticated and versatile force measurement systems, enabling us to explore the world around us with greater precision and understanding. So keep your curiosity piqued and your eyes on the horizon. The future of force measurement is brimming with exciting possibilities.